You've just mentioned that you'd like to stop writing all your kind of build definitions, all this boilerplate, and focus more on just what the commands are. Well, here is the answer. So today I'm going to talk about Rattle, and we've seen lots of work on build systems at kind of the Bazel scale, the Grab, the Netflix scale. But what about slightly smaller use cases? Can we do better for those? So let's think about kind of what we need to write down to compile two C files and link them. Well, we can create a little shell script. Let's call it make.sh. And all we need to do is gcc -c main.c, gcc -c util.c, and then link them together. This is a perfectly good little script for building two files, but it has some downsides. It was very simple to write, and we have full control over the commands we're executing. Whether that full control over the commands is a good thing or a bad thing is maybe a discussion for later. But if we look at a build system, if we tried to write a similar thing in Bazel, it would have been vastly more complicated, and we would have had to be very careful about specifying our dependencies, e.g. what header files do those two C files pull in? What's the toolchain? Which GCC version are we using? When does that GCC version change? But in return, a real build system will give us parallelism, the ability to do the two C compiles in parallel, and incrementality. When a header file changes that's only used by one, or when a single C file that changes, it will only build just that C file and redo the linking. But what if we could get the advantages of the build system with the simplicity of the shell script? And that's where I introduce Rattle. So if I run Rattle on make.sh, I get parallelism, incrementality, and cloud builds all for free. I didn't have to write any dependencies, it just worked. So Rattle was introduced in a paper called Build Systems with Perfect Dependencies at OOPSLA 2020, which was joint work with my co-authors, Sarah and Sam. So you can read that if you want to see the full details, but this is just kind of highlights. So if we've got a series of commands in a file, how can we get incrementality? So first off, Rattle assumes a slightly more general method than just a series of commands in a file. It assumes there's some kind of system producing commands for you, and in particular, the future commands that are produced might be dependent on the results of the previous commands. So it could say run gcc ---- version and use that to make a decision and decide what commands to run, say whether to add a specific flag or not. This gives it the power of dynamic dependencies that we saw a lot in pants earlier. Now, once we've got this model, to get incrementality, it's not too difficult. For each command, Rattle uses FSA trace to record the inputs and outputs. And FSA trace works by a variety of methods depending on the platform and the configuration options. For example, system call hooking, LD library preload, Windows hooks. And FSA trace tells us at the end of the command, these files were read and these files were written. To get incrementality, all we need to do is hash the inputs, hash the outputs. Next time we encounter the same command, if the inputs are the same as last time, and all the inputs have the same hash, and the outputs all have the same hash, then we don't really need to bother running the command. We can skip it. This assumes that commands are deterministic, so that the result of them is only determined by their inputs in command line, but Rattle has ways to flag commands as not being suitable for this. So Fabricate was one of the first build systems to do this trick, probably over a couple of decades ago, but didn't really take off. Sadly, I think it's a nice model. How do we get cloud builds? Well, given what we've done for incrementality, we've got a list of commands, a list of their inputs, and a list of their outputs. All we have to do is store the inputs and outputs in a cloud cache. And when we've decided that we do need to run the command, we then decide, when we decide we do need to run the command, we see what other files are required, see if it's already in the cloud cache. This isn't as quite as simple as it seems. It isn't the Bazel model, the remote execution model, where you just look up the command and its hashes by SHA and find the outputs, because depending on the commands, there might be multiple different sets of inputs that match. But in worst case, you can just scan for a match. So we've got cloud builds. That bit was easy. How do we get parallelism? Now, parallelism is the tricky one. With this model of having a stream of commands, we don't know what commands are coming next. But if we guess what commands are coming next, presumably by looking at the history of commands, we can run them and see if they were right. And if they were right, we save some time. So we had a whole talk on speculation earlier. And if you think of it as kind of like CPU speculation, that's not a bad model. Whenever we have a space, some local resources available, we will speculate on what we think is the most likely thing, and remember that result. And if it's useful, we'll actually use it. However, unfortunately, we're using local execution. So when we run a local execution, that may read a file that hasn't yet been produced. That may be write to a file that another command writes to. And in the paper, we go over what properties the build system needs to ensure that's correct. And we define a whole concept of hazards, which say when two commands conflict. And then we prove a bunch of necessary properties so that you can know that a build was correct with respect to hazards. And if hazards do trip you up, you have to rerun a command. And that will give you a speed hit. So you did some work, the speculation was invalid, so you have to wind back and now do some more work, so it'll go slower. So does that actually work in practice? Well, we took a bunch of examples, but I'm going to focus on two in this talk. So FSA trace is a small C program that does tracing of dependencies. It's about 20, 30 odd C files. And what we did is we took the last 50 commits and we compiled them successively using the incrementality and the parallelism. And as you can see, the make build system, which has full dependencies and was carefully written and tuned over time, versus the Rattle system, which is just all the commands in an order that is valid, but not particularly carefully done, with a lot less information about dependencies. If you look at the two graphs, Rattle and Make basically perform the same within a few percent, apart from in two places, which I've circled in green. The first build, Make can use its dependency information to give parallelism. So Make with 4 threads is quite a bit faster than Rattle with 4 threads. Because Rattle, the first time round, there's nothing for it to speculate, so there's nothing for it to do. On the second build on this graph, Rattle hit a hazard, so I had to redo some work. So Rattle was a bit slower there, but we've specified a lot less. We've had a much easier time working with our build system, and we've got roughly the same performance. Now let's look at Node.js. Node.js is a much bigger project, has a lot more complication, a lot of features like it compiles in a memory allocator and other things, runs configure scripts. And if we look at this, Rattle is in red and Make is in blue. And you can see Rattle is the same speed or quite a bit faster than Make in many cases. And the reason this is that Rattle's build dependencies are correct, whereas the Make ones are very difficult to specify correctly. So there are both overbuilds and underbuilds. But Rattle gets it right because you don't specify dependencies. It's not your job. So it is correct by construction. The one problem we have is the very first build, Make can get parallelism while Rattle can't. But if you use the cloud caching feature, you only ever have to do the first build once and once only. So I entitled this talk, Rattle, a build system for small use cases. So why did I say small use cases? Well, firstly, Rattle is an immature technology. It isn't in use at Netflix and Grab, etc. It's it's an example that is used a little bit, but not very much. The other reason is that Rattle requires you to give a single linearizable trace of all the commands in your build system. For simple systems, that's super easy and much easier than writing the build system with dependencies. But doing it compositionally at scale, often the easiest way to specify the linearizability is through dependencies and auto-generating it, and then you're starting to get back to a traditional build system. So I like to think that Rattle makes it super simple to do a super simple build system, and it's possible that for small open source multi-language projects, where small can be as large as Node.js, Rattle might be the right build system to use. Thanks very much, and I'd welcome any questions.
Neil, that's fantastic. Look, the build system that infers everything as a result of my crappy shell commands to build the first 3 files that I put in, that's what I've wanted forever. So we do have a couple questions. Let's see if I haven't removed the archive. Regarding Rattle, what are some obvious next step improvements that operating systems, and the parentheses here is Fuchsia, could provide in their process or file system APIs to make Rattle's job easy?
Well, so this area is really poorly served. So system hooks and stuff isn't the right way to be doing this. It would be very nice if you could subscribe to a stream of what a process was doing in terms of file reads and writes. So with FSA trace, we get the list at the end. So that means there are some hazards that aren't real, but we have to assume all reads occurred right at the beginning of the process and all writes right at the end. No, all writes at the very beginning and all reads at the very end to get the most conservative approximation. So just knowing when an actual read and write happened would be great. But really just being able to do this without hooking system libraries and stuff and working reliably on Mac would be very nice too. It's, Mac keep locking down their thing with security considerations, making this harder and harder. So yeah, there's loads operating system developers could do. In the same way they've taken steps towards things like iNotify, this is another area they could really help with.
Look, if anybody out there hasn't tried to do what Neil is doing or like similar activities, go try the ptrace API, because I've written a couple of things to do this, and just like he's talking about with LD preload and the activity going on, and actually ptrace will allow you to do this with a completely distinct process if you have that access level. Again, if Mac hasn't knocked it down for you, in order to completely capture all of those system calls. So
yeah. FSTrace also has a ptrace backend, and we switch them based on performance and other considerations.
Yeah, I mean, the advantage of the ptrace one is that you get it live. Like you can literally stop that program from doing whatever it's doing, and then wait, until your processing is completed before you enumerate the file and keep track of that thing for going forward. So our next question is: you've got Shake, now Rattle. Is there a role?
Yes, almost certainly, but maybe not for another decade.
Okay.
No.
Is that an android from the Mega Man trilogy?
No. Shake, rattle, and roll is just kind of a standard phrase. I think from rock and roll, maybe Chuck Berry or someone. I don't know. It predates me by many, many decades.
It predates me by less, but I'm okay with that. Are there any thoughts to using Rattle to bootstrap or track or generate inputs to a more complex build system? Meaning, presumably, generate build files?
In a way, what Rattle has done is generated a build file for itself that it believes might go out of date at some point in the future. So I'm not sure you would particularly use it to generate a build file, because you'd want to keep regenerating it, and then you've got the whole generated problem that we saw in the previous example.
All right. So can inferring dependencies yield? Whoa. I'm sorry. It's late in the day. These are big words. Can inferring dependencies yield to involuntarily false dependencies without noticing it? For example, leading to broken encapsulation and tech debt. In contrast, I think they're comparing here a build system with explicitly defined dependencies is able to tell you what is wrong.
Yeah, I mean, I think this is a standard thing. If you write it in two places, the chances of someone inadvertently changing it without meaning to vastly decreases. Like in Bazel, I'm unlikely to drag in a header from another library without realizing I did it because I've got to update the header file and then the targets file. If I only have to specify it once, that's great for not repeating yourself, and it's also not great for making mistakes because I only wrote it once and nothing checked it. So trade-offs.
Awesome. All right, Neil, we're out of time, out of questions, and I applaud you for developing such a great tool and using such a great thing like FSA Trace and ptrace. Looking forward to your next talk and the discussion of role and whatever else, shake, shimmy, bang, boom, whatever else we can run.